Oh, acid solutions conduct electricity, acids don't. Thank you. It is relatively weak acid, isn't it? Okay. Yes. Now, the other acid I have is hydrochloric acid. Tell me what you know about hydrochloric acid. It's a relatively strong acid. Now, let's talk about what that means as far as dissolving it in water. I have three different concentrations. This is 0.1 molar acetic acid. This is 0.01 molar acetic acid. This is 0.001 molar acetic acid. Yes? I made this by taking 100 milliliters of this and diluting it to a liter. Increasing the volume 10 times, cut the concentration to 1/10 as much. I made this solution by taking 100 milliliters of this and diluting it to a liter with deionized water. I did the same thing here, except that the concentrations here are going the other direction, 0.01 rather than 0.1. This is 0.001. This is 0.0001. This is 1/10,000th of a mole per liter. Okay? You'll see why the concentrations are different in a second. Now, first of all, we know that water, this is deionized water, does not conduct electricity, right? Okay? Just a quick reminder of that. Water does not conduct electricity, right? Not very well, anyway. Okay? However, a solution of hydrochloric acid, this is the 0.01 molar, conducts quite well. Why does this solution conduct electricity quite well? Because it has lots of ions. We know that water conducts electricity if it contains ions. Does it make sense that the higher the concentration of the ions, the better it conducts electricity? Okay? Now, here's the equation for the reaction of acetic acid. Acetic acid is one of our organic acids where the acidic hydrogen is listed at the end rather than the beginning. Okay? It's quite common also to find the hydrogen listed in front, like other inorganic acids. It's quite common for this formula to be written like this. CH3COO. It's also common to see this acid written like this. Okay? You know, I'm telling you that because standardized test coming up, right? You'd think there, on a standardized test, there'd be a nice standard way to write everything, right? Well, there's not. One of the things that drives me nuts. We'll talk more about those later. So there's the reaction for acetic acid dissolved in water. Here's the same reaction for hydrochloric acid dissolved in water. And as you can see, the reactions look very, very similar to one another, don't they? Right? Which is the stronger base? We're having a tug of war, aren't we, between two bases. The base that starts out with the hydrogen on this side is called the acetate ion, and it has the hydrogen ion attached to it. The water molecule is trying to take that hydrogen ion away, right? In the backwards reaction, we have the water molecule with the hydrogen ion attached, and the acetate ion is trying to take it away. Who's going to win the battle more of the time? The stronger base, huh? And which is the stronger base? Water or acetate ion?
Acetate.
Acetate ion is the stronger base. Does that make sense? Based on what you're looking at in the table, right? Okay? Now, let's look at this reaction. Here we have a chloride ion with the hydrogen ion attached, and the water molecule is trying to take it away. Over here, we have the water molecule with the hydrogen ion attached, and the chloride ion is trying to take it away. Yeah? So, we have a competition between two bases, tug of war between two bases. Which base is stronger? Water is this time, huh? So where do the hydrogen ions want to spend most of their time in the acetic acid solution? With the acetate ion, huh? In this solution, the hydrogen ions want to spend more time with the water molecules. So we end up with a lot of these, and not very many of these. Over here, we end up with a lot of these, not very many of these. Yeah? Because the hydrogen ions want to be with the stronger base. Yeah? Bronsted-Lowry acid-base reactions are all about the bases. How strong are the bases? In a Bronsted-Lowry acid-base reaction, bases are competing against one another for the hydrogen ion, aren't they? And what we're interested in is who's going to win most of the time. How are we doing? Okay? Now, joking. Lost track of my beakers here. Now let's see, this is a 0.01 molar solution of hydrochloric acid. This is the 0.01, wait a second, 0.01. This is the 0.1 molar. I want the 0.01 molar solution. These two have the same concentration. This one has the weak acid in it. Okay? Same concentration, same number of moles of the acid per liter of solution, but the acetic acid doesn't conduct electricity nearly as well. Why? Because in the acetic acid solution, most of the acetic acid molecules still have their hydrogen ions attached to them. Only a small percentage of them have managed to have their hydrogen ion taken away by water molecules. Whereas with the hydrochloric acid, almost all the HCl molecules that were dissolved in that solution originally have lost their hydrogen ions. Almost all of them. So we end up with more ions here, huh? Every mole of this that gives up its hydrogen ions produces a mole of each of these. How are we doing?
Wait, can you go over where the hydrogen ions go so that the hydrochloric acid conducts electricity?
So the hydrogen ion starts attached to the chloride ion as a neutral molecule, huh? So if none of these molecules gave up their hydrogen ion, then the solution would not have any ions in it, would it? It would have neutral molecules only. So if this gave up its hydrogen ion to make hydroniums and chloride ions, then we'd have more ions, right? And that's what we had. With equal concentrations of the